Hello. Okay, so welcome everybody to this new seminar. Today is a real pleasure for me to introduce our speaker, Yael Aidelman. She is a researcher, astrophysicist from Argentina, working for the Consejo Nacional de Investigaciones Científicas y Técnicas, the Universidad de La Plata, there in Argentina, and she's part of the research group Modelos de Estrellas Peculiares, so stars with peculiar stars. She did her PhD in 2016, so 10 years ago already, with a title called Population of BE stars in open clusters from our galaxy. You will learn about these BE stars today. And her research is mainly focused in the spectrophotometric study of massive stars, and in particular B-type star with emission lines, where we have the B stars and the B supergiants. And she's developing there now in the Universidad de La Plata. She's also the coordinator since 2019 of a very interesting project that is called Recuperación del Trabajo Observacional Histórico, and is basically a group of people that is putting efforts in the recovery and digitalization. I don't know if this is correct word in English. Digitalization of spectroscopic observations made long time ago with photographic plates. So it's a very interesting project. And it's also a representative for the Universidad de La Plata in the user committee for the Complejo Astronómico Leoncito, that is a very important observatory there in Argentina. So she has been here already for almost 2 months. Yeah, she will be traveling to La Palma next week, and then will be here for 1 week more or less. And she has been here as part of a very interesting project that now is active, that is called Oceans, Overcoming Challenges in the Evolution and Nature of Massive Stars. That is a project funded by the European Commission to help the connection between Europe and South America. So there has been many researchers from Argentina, Chile, and Brazil coming here, and also we are going there. So I'm very happy to have you here today. So whenever you want, you can tell us about your research.
Thank you. Can you hear me? Okay. Okay. So I am Yael, and first of all, I would like to thank you to giving me the opportunity to talk about my work here. And today I am going to talk about the BCD classification system based on in the Balmer discontinuity and its application to B-type stars with and without emission lines. I am working in La Plata Astrophysical Institute in Argentina, and I am a member of a Peculiar Star Models research group. And our research focuses on B-type stars from both observational and theoretical points of view, taking into account the wind structure and the solution of the radiative transport equation. So the B-type stars are stars that have temperatures between 10,000 and 30,000 kelvins and masses around between 3 to 20 solar masses. And they show radiation-driven winds that lead significantly mass loss throughout their evolution. And in this way, this star contributes to the chemical enrichment of the interstellar medium. And in some phases of their evolution, and even during the main sequence stage, some B-type stars show emission lines in their optical spectra. And for this reason, they call emission line B-type stars. And generally, these stars are embedded in dense gaseous environments, and also would have dust in dust environments. These envelopes causes the line emissions and also an infrared excess. In this group of this star, we can find objects in very different evolutionary stages, such as Herbig AEB stars, which are pre-main sequence stars, classical BE stars, which are non-supergiant stars with rapid rotation and circumstellar disks, also blue supergiants stars, which have very extended atmospheres, and luminous blue variable, which are post-main sequence stars characterized by intense eruptive mass loss event. As these objects can show very similar spectroscopic features and similar color indices, determine its evolutionary stage and stellar characteristics are very challenging. So for this reason, we propose the BCD spectrophotometric classification system to study this type of objects. The BCD method was developed by Barbier, Challenge, and Divan, and they propose a classification system based on the morphology of the Balmer discontinuity. Daniel Challenge start the study of the spectroscopic in the wavelength range around the Balmer jump in 1934. And he developed a spectrograph to carry out his research. The Balmer discontinuity is stellar continuum spectra characteristics, and it can be interpreted as a way to measure the balance between the neutral hydrogen in the photosphere versus the ionizing photons emitted by the deeper layers of the photosphere. So for this reason, the maximum of the sham is in A0 type stars. And for hotter stars, the Balmer discontinuity of the sham is lower because the hydrogen is fully ionized. And for cooler stars, the sham is lower because the photons do not have enough energy to ionize the hydrogen. So Barbier and Challenge in 1939 proposed for the first time a way to measure the sham. They proposed two observable parameters. D is the height of the sham, and lambda1 is its mean position. To measure the D value, we use the extrapolation of the Balmer Paschen continuum to 3,700 angstrom. And from the blue side, we use the Balmer continuum at the same wavelength. And Balmer lambda1 is the wavelength corresponds to this point. This point is the intersection between the upper bounding curve of the Balmer lines and the straight line parallel to the patient continuum, but this line pass through the midpoint of the jump. And some years later, these authors added a third parameter, phi, that is the color gradient, and its value corresponds to the slope of the patient continuum and is defined for different wavelength ranges. This value, phi, the color gradient, is affected by the reddening, so it can be used to estimate the absorption, the visual absorption. Shalom and Divan derived an empirical relation between the visual absorption and the difference between phi and phi zero. This phi zero is the intrinsic color gradient, and that is the color gradient without reddening. And from the research of the authors, we can consider that D and lambda 1 value are independent of the reddening. So this method allows us to estimate distances. Using these three BCD parameters, D, lambda 1, and phi 0, the spectral type and luminosity class is unambiguously determined. This is because D is related to the effective temperature, lambda, and it has a maximum for A0 type stars. Lambda 1 is related to the surface gravity, being lower to the supergiant. And phi 0 is related to the color temperature, and it's increased continuously from spectral type O to F. This is a picture of the surface made by hand by Barbier, Challenge, and Divan. This plot is a projection over the plane of the surface I showed before. In this axis, we have the D value, and in the vertical one, we have the lambda 1 value. So with D and lambda 1, we have a point in this plane, and each square corresponds to a spectral type and a luminosity class. This, the left side of the plot corresponds to a hot stars, and the right corresponds to late A and F stars. Some years later, Sorek made similar calibrations to for surface gravity, volumetric magnitude, and absolute visual magnitude. Each calibration has in the horizontal axis the D, and in the vertical one, lambda 1. And each curve corresponds to one value of the parameter. So these curves are like level curves in the plane. And some years later, Sorek improved the calibration for the effective temperature and for the B spectral type. So when I start to use this method, I had to print the spectrum, and I had to use a ruler and a pencil to measure the D and lambda 1 value. So when I began my PhD, I decided no more pencil, no more rulers. So that is how MIDE 3700 was born. And this software allows us to measure the BCD parameters in an interactive way. So when you run the software, you can choose the points to make the fit, and we can fit the Paschen continuum, the Balmer continuum, and the bounding curves. And also we can deselect points to improve the fit. And also we can use these lateral buttons to select the best fit. Then we can repeat this methodology, but on the spectrum normalized by a black body to improve the D measurement. And finally, the software give us the D lambda 1 and phi values. And then it performs the interpolation in each calibration to calculate the stellar parameters. And also the software can calculate the absorption and the distance, as we can see in this example. So this is the method. Here I list an examples in where the BCD was applied in very different B-type stars. And taking into account that D and lambda 1 values are redundant-free, this method is ideal to apply in emission line B-type stars. So today I show you two examples that I use the method. So the first one is the study of B-type stars in open clusters. So I observed 230 stars belonging to 11 open clusters. And using the BCD, I estimate the spectral types, the effective temperatures, surface gravity, and absolute magnitudes, and also the color excesses and the distances for all stars in the sample. Here is a table of the open cluster NGC 2645 and the sample star belonging to this cluster. And along this study, I also observed BE stars in these clusters and study the Balmer region, the Balmer jump region in BE stars is very interesting because some of these stars show a second Balmer discontinuity. In some cases, this second Balmer discontinuity can be in emission, in other cases in absorption. Divan explained that this second Balmer discontinuity is related to the circumstellar envelope and is a shift to a bluer wavelength because the density in the disk is lower than the photosphere. So the first jump and the second jump are clearly separated in the spectrum. And so to estimate the stellar parameters of the central object, we use the first jump, and the first jump is always in absorption. So using the first jump, we can estimate the parameter of the central object. It is important to note that not all BE stars show the second Balmer discontinuity. Other interesting thing that I found during this study is some B-type stars show a second Balmer discontinuity in their spectrum, but were not reported as BE stars. So these kind of stars do not show H alpha in emission. So, but the second Balmer discontinuity confirms the existence of a circumstellar envelope. So we propose for this kind of stars that the disk will be more compact than the BDD stars. And we labeled BDD stars, and the double D is because double discontinuity. So the main result of the study is that we confirm that the B phenomenon appear in the whole main sequence stars. In this plot, we have the effective temperature and the surface gravity for the stars. And also the B stars appear in different evolutionary stages. And also we found a relation between the amount of B stars with the cluster age and the maximum of the stars with circumstellar envelopes appear in open cluster with intermediate ages. And a little thing that I want to explain is the younger open clusters have late B-type star here in the blue bars, but the late B stars with circumstellar envelope appear in the older cluster. So this result would be indicate that for late B stars, the development of the disk take longer. A spin-off result of this study is we found two supergiant stars, this one and F with F spectral type, and this one B with B spectral type belonging to open cluster that show the second Balmer discontinuity in absorption. So we began a search of this kind of stars. And for now, we found 6 more. So we have a sample of 8 supergiant stars with a second Balmer discontinuity in absorption. So our interpretation is this supergiant have a circumstellar envelope, but we still don't know its origin, but I'm working on it. So it's an open final. Here I show a plot here in the horizontal axis with the is the effective temperature, and in the vertical one is the height of the second Balmer discontinuity. And I plot BE stars belonging to open clusters and fill BE stars from the work of Chetty. And here we can see that stars cooler than 18,000 show the second Balmer discontinuity in absorption, while the hotter stars show the second Balmer discontinuity in emission. And there are several PE stars that, without a second Balmer discontinuity. So the interpretation of this plot is that the height of the second Balmer discontinuity can be used as a tracer of the characteristics of the disk, because the difference between BE stars with second Balmer discontinuity in absorption against those with the second Balmer jump in emission could be related with the temperature of the environment, the circumstellar environment, being this one hotter than this one. And also, the difference between the stars with the second Balmer discontinuity and without could be related with the density of the environment. So big stars without a second Balmer sham would have low dense disks. And then the second example is the application of the PCD method to a massive stars in transition phases with without second Balmer discontinuity. Here we have a sample of 14 stars like Herbig, B bracket, and LBB stars. And also I added the classification available in the literature. So to emphasize that it's very difficult estimate the nature of the central object. For example, for this star, it was classified as prime sequence object and also as a Ball object. So we apply the visiting method and we derive the stellar parameter of the central objects. And also we estimate the color excesses and the distances for all stars in the sample. And to discuss the evolutionary stage, we use the theoretical HL diagram, the spectroscopic one, and two mass color diagram. In this plot, these gray points corresponds to the luminosity if we consider the distances estimated by variations from the Gaia galaxies. And here the gray point corresponds to the location corrected by Aidelman. So using the stellar parameters and the location in this diagram, we discuss the evolutionary stage of this object, and our results confirm the classification for some of the stars, and for the rest of the stars, we propose only one classification. And for these two stars, we published for the first time the stellar parameters. So my final conclusion of this talk is that the PCD method is a powerful tool to derive stellar parameters, and principally for emission line B-type stars. So thank you very much.
Thank you so much for a very interesting talk. Are there any questions in the room or online?
Thank you very much, Yael. Since we have been discussing about this, I have a question about how this is connected with the information you have from images and from photometry. So, I mean, the first thing is there any study or you have done any study to see if there is in images of these stars like signatures of some circumstellar material in
He found the stellar envelope in Cheyenne. No, okay, I missed my. But my relation with the No, I didn't.
But it's something that would be interesting to do like a survey with images in the corresponding with the corresponding filters to see if there is a correlation between those where you find the double discontinuity and the
Are very different objects, so it's difficult to see the circumstance. Yes.
And then the second question is sometimes photometry is used as a first approach to get temperatures of the stars but then, and this is based, for example, if I understand correctly, if you use U and B, you are kind of also measuring the effect of the Balmer jar. But now you show with the spectra that sometimes you have this double discontinuity. So obviously, this is something that has to be taken into account for this photometric determination of temperatures in B-type stars, because there will be an effect also.
You you are sure the complete the total sum. That is for example, where is it? Here. When the second Balmer activity is in absorption, this height is positive. And when it's in emission, no se escucha. Bueno, it's in emission. The height is negative. So if you, with the U minus P color index, you are measure the height of the first shunt plus the second one. So if you have the second Balmer in emission, you are measure a lower index. Yes, but for another hand, the envelopes causes infrared excesses. For this reason, the infrared filters can be help to disentangle this question. I made a study using the Q parameter from the color indices to help to disentangle the massive star in transition phases. And it will be very interesting. And the D value of the height of the first Balmer jump is correlated with the Q parameter. So yes, the both techniques we can help to.
Thank you. Any other questions? Okay.
Thank you so much. Yeah, it was really nice. I'm curious, and maybe this is a naive question, but is it hard to distinguish this difference in the Balmer jump with, say, a binary companion?
Yes, if you have a companion, you can distinguish the Balmer jump, but I suspect that the Balmer jump is affected by in a binary system because you are seeing the spectrum of both stars together. So it's necessary to study what star is contributing to the jump. So if you have the two component equals with similar spectral type, is no problem. But yes, I began a study to measure the second Balmer discontinuity in a binary, but I didn't finish yet. So yes, it's interesting because we suspect that if the system have mass transfer, perhaps we can see changes in the second Balmer discontinuity. So yes, it's very interesting.
Thank you. Any other questions?
So yeah, thanks. Great talk. I was wondering, maybe you mentioned it, what is the requested resolution of the spectra for the BCD method to work? Okay. And also with the distance uncertainty, I guess it will be related to the resolution, the distance that you can estimate, and how it relate the value of the uncertainty in the distance, the error in the distance, with astrometric methods, for example.
Yes, the uncertainty in the distance, I think is a little bit higher than the photometry, because the measurement errors in D and lambda 1, ¿cómo lo digo? Se va transfiriendo, sí. So in the absolute magnitude, the error is, yes, is greater than we want.
Thank you. Are there any other questions?
Thanks, Yael. I have questions about the second discontinuity. So the DE phenomenon, we don't always detect the disk. So do we detect any change in the second Balmer discontinuity? I mean, do you have any star that is going from absorption to emission, for example, in this discontinuity? Like you have stars that are in absorption and stars that are in emission. Do you have any star that it's transiting from absorption to emission?
Yes, in the older papers, the Barbier, Challenge, and Divan, yes, they show stars that changes the second Balmer discontinuity from the absorption to, and the second Balmer discontinuity disappear and then appear in emission and so on. Yes.
Okay, so this connects with a second question, which is in the graphic, which you show the relation between temperature and the height of the second
Yes.
discontinuity. Yes, this one. How are those stars? Because I guess that the temperature does not change, so they are going from one side to the other, aren't they?
Okay. No, I don't remember the effective temperature of those stars. But the other problem is that the older papers do not measure the height of the second Balmer discontinuity, so I need to repeat this observation to can measure the and see where are these stars in. But perhaps with the effective temperature, we can imagine.
Yes, the point is that you have here like two, let's say, avoidance regions, two regions in which you don't have stars, which is under 18,000, you don't have stars that are in absorption.
Mhm.
And over 18,000, you don't have stars in emission. But you may have some stars that are transiting between those zones, I guess. aren't
Here,
they?
in oh, oh, ¿qué pasó? Ah. No sé qué fue. In the plot, is a band between 50,000 and 80,000 that is here. No. ¿Qué pasó? Here. So here, between 18,000 and 15,000, there are stars with emission, with the second Balmer emission. So I think it's a band where both can be exist. But I don't know where is the B stars that changes. I can see later.
Yeah, that may be interesting. And then the last, what is happening at 18,000,
I
like
don't-
physically?
I don't know. I want to begin a study and reobserve several stars to measure the second Balmer discontinuity. And yes, and because I don't know if this tendency is real or is a bias. But yes, it's interesting because the behavior is very different because here seems to be a linear relation, but here, no. So yes.
Yeah, thank you.
Very interesting, very useful, yeah. And maybe I miss it, but you were talking when you were talking about the method and fitting the lower part of the peaks of the hydrogen lines. You said you can choose the best one.
Yes.
How do you select the best one? Why do you select this?
Okay. Yes. Yes, thank you for your question because I realized that I forget say mention this. So in here, okay. In normal stars, the upper and lower bounding curves of the Balmer line and the Balmer continuum in 3,700 converge to the same point. So the Balmer continuum and the lower bounding curve define the base of the jump. So when you have the second Balmer discontinuity, so we use only the lower bounding curve. And we can decide the best fits using this criteria that the upper and lower bounding curves, yes, need converge to the same point. So in some cases it's difficult, but if the star is normal, it's easy.
Okay. Are there any other questions here or online? No? Okay, well, if there aren't, let's thank the speaker again. And just remind you that there will be coffee in the cafeteria so we can continue the discussion there. I think I have all the PhD students written down, so don't worry.